My name is David Teitelbaum. I'm the program manager for the WPF graphics team. The title for today's talk is Windows Presentation Foundation, Extensible BitmapEffects, Pixel Shaders, and WPF Graphics Futures. And I'm going to go through and kind of correct the title and the abstract for this a little bit, because the abstract basically described everything under the sun that I was going to be talking about in this lecture, and I really don't have time for that. So if we move on to what I think the title should be, it would be Extensible Shader Effects, which are effectively pixel shaders, DX interop, and WPF graphics futures. And you notice by the size of the fonts, I'm trying to kind of emphasize relatively what I'm going to be talking about and what I'm not going to be talking about. The bulk of this talk is going to be about shader effects. I am going to talk about DX interop to the extent where I think everybody should understand DX interop. After the talk, I'll show demos of this stuff. And I'll talk a little bit about WPF graphics futures, but I'm not going to go into too much detail. And I want to kind of set the stage up front. I don't want to disappoint a lot of people, but a lot of these features are still in the development phase, and it would be premature to talk too much about them. I can give you kind of a rough overview of the direction we're going in, but I'm not going to go into real excruciating detail. I don't have prototypes for a lot of these things. So that having been said, thank you for coming here. The gods of scheduling obviously hate me, which is why they put me in the last time slot on the last day of PDC. So it's very gratifying to actually see a crowd this large turn out for a talk like this. It's exciting to see that WPF is actually showing a lot of interest in a lot of people. And a little bonus here, since it's the day before Halloween, I figured I would bring my Halloween costume. And so if you want me to take this off, I mean, show of hands, I don't want to annoy people by wearing this. If anybody wants me to take this off, just let me know, and I'll take it off right now. Otherwise, I can leave it on until it gets so annoying to me that I have to take it off. But, okay, I guess nobody's really angry at me, so I'll continue. So the high-level points of what I'm going to be talking about today. I'm going to talk about the motivations for our new effects system. Most of you, I would assume, are familiar with our original effects system, the BitmapEffects system. It was introduced in WPF 3.0, and it's got a large number of caveats. I'll go through those. I don't want to kind of dwell on it because there is a lot of new stuff I want to talk about. But we'll be talking about the old effects system. I'm going to give you a really quick HLSL primer. HLSL is the language that you write pixel shaders with, and that's how you write the new shaders that we've exposed in WPF. I'm going to talk about how they're exposed through managed code in WPF, because in WPF there are two components to one of these new shader effects. There's an unmanaged HLSL component, and there's the managed component that wraps everything up. And then I'll talk about DX interop a bit. It's our new class called D3D image. And then I'll talk a bit about the coming graphics features in WPF 4.0. So why are we going to a new effects system? What was wrong with the old effects system? It was introduced in 3.0. I don't want to talk about this too much because, again, I've got a lot to cover here. Basically, you could apply a bitmap effect to any UI element in your scene. It would apply some kind of an effect like a bevel or a blur or whatever. And there was an extensibility mechanism. So if you wanted to, you could go ahead and write your own effect. Your own effect was written such that it would run on the CPU rather than the GPU. And so you weren't getting any of the hardware-accelerated benefits of WPF. Now, when you applied an effect to your scene, what we would effectively do is we would take the entire subgraph of the element that you would apply the effect to. We'd render it into a software intermediate render target. We talk about hardware and software intermediate render targets. It's basically an off-screen surface that we're rendering that entire subgraph into. And then we have to use our software rasterizer because it's being rendered into a software render target instead of a hardware render target. You might be asking, why don't you just render it in hardware and then suck it back into system memory if you have to run your effect in software? The reason for that is that we didn't want to do hardware readback in the effects system. There were several reasons for this. One was that the original remoting mechanism in WPF was a lot like the X Windows remoting mechanism, where we remoted primitives, and you could have the client machine and the application machine be thousands of miles away connected via network. And so your display machine would then effectively be rendering your bitmap off screen. It would have to send it over the wire back to your application machine, which would then be running the bitmap effect, and then that would send that back over the wire to your display machine again. So that would be extremely slow from a network latency perspective. Other reasons are that a lot of the buses on the older video cards were extremely slow at readback. AGP was very slow. PCI was even slower than that. It's only with the advent of the newer buses like PCI Express that we really have fast readback from video cards. And at the time WPF was originally conceived, which was 5, 6, 7, however many years ago, the commodity hardware was all AGP. So this rendering into a system memory bitmap is analogous to render target bitmap, if you're familiar with that. It's just taking a subgraph, rendering it via the software rasterizer into an intermediate render target. You'll notice that there are some limitations with intermediate render targets. And this doesn't just apply to BitmapEffects. This applies to drawing brushes and visual brushes, but it also applies to BitmapEffects. So I'll just go ahead and list them right now. If you use something with a bitmap effect applied to it in 3D, we don't generate an entire bitmap chain for it. We're not doing anisotropic filtering for it, so you'll notice that the quality, especially when the thing is, when there's a very sharp angle on your surface, is not as good as it would be with an image brush, for instance. And there's no clear type in intermediate render targets. And I actually didn't understand why there was no clear type for about 2 years, and I came to understand it last Friday. And effectively, the reason is you're rendering at 3 times the horizontal resolution, and you would need an alpha channel per color channel on your bitmap in order to get correct clear type rendering into an intermediate render target. And since there's only 1 alpha channel per 3 color channels, because you have ARGB in your intermediate render target, you have 1 alpha per 3, you can't correctly render clear type text into a standard pixel format if you're rendering into an off-screen render target like this. So then I guess I've already gone through the rest of this. I mean, you're rendering on the CPU rather than the GPU, and after all that was done, you would composite it with the rest of your scene. And here's the old syntax for how you would use a bitmap effect. I've got an image. I'm putting an outer glow bitmap effect on it. The image is very cute, and you wind up with a cute cat that's glowing. Very exciting. So the performance caveats, I've already gone through these, so this will be a quick slide. Software rendered. The whole subgraph is rendered in software, not reading back. And then another reason they're slow, and this is something that's kind of non-obvious, this is that blur operations are typically very slow, whether they're in software or in hardware. And the most popular bitmap effects in WPF are all blurs. They're drop shadow or blur, and then glow is another one. These are all behind the scenes being implemented as a blur. Now, the reason blurs are so slow is that for every pixel you're writing, you actually have to read from a large number of source pixels. And it's a function of the blur radius, and it actually grows as the square of the blur radius. And so everybody loves drop shadow, but drop shadow is extremely expensive, and it's even more expensive in software. So that was why you kind of hit the performance bottlenecks you did. So what did we do? In the service pack we just released a few months ago, we marked software bitmap effects as obsolete. So if you compile in Visual Studio, you'll get this obsolete warning. We added what we call a hardware fall forward to the blur bitmap effect and drop shadow bitmap effect. So if you have a blur bitmap effect in your scene, even using the old API, as long as your parameters are within allowable limits, like your blur radius isn't too big, as long as you're not using it in the bitmap effect group, and there are a few other characteristics that you can just look up on MSDN and find, then you'll get this hardware fall forward where we actually will hardware accelerate it. And moving forward in WPF 4.0, which will come out sometime in the near future, we're actually going to be removing the software bitmap effects pipeline. So this is something you should be aware of, because if you're using one of these software bitmap effects and there's no hardware fall forward for it, it's going to effectively be a no-op. So you could apply an outer glow to your element in your scene, and it will just act as though there's no bitmap effect applied to it. So plan ahead with this. With 4.0, you're going to have to target your application to build for 4.0, so this isn't going to just come up and sneak up on you, but you should be aware of it. So in designing our new effects system, we had a number of goals in mind. The first and biggest was that we wanted them to be GPU accelerated. We wanted the entire subgraph to be rendered in hardware instead of software, which means we're rendering to a hardware intermediate render target rather than the software intermediate render target. And we also wanted to hardware accelerate the most popular effects, which were blur and drop shadow. We would have liked to have accelerated all of them. We just basically ran out of time. So we took the 2 that were most popular and we accelerated those. Another requirement of our new system was that we wanted people to be able to write their own custom hardware accelerated effects. Before you could write your own custom software effects, and they were used in a limited number of cases, but again, they were rendered in software, so they had all the performance characteristics. And we wanted the fast software fallback pipeline. This is actually faster than the pipeline that we had in the original BitmapEffects. Our new one is using SSE2, which means it only runs on machines that have SSE2, which is basically any new machine. The only machines I can think of that are even moderately recent that wouldn't have SSE2 would be Athlon XPs, and those are 5 years old. So basically any recent machine can do our software fallback. Another requirement was that we wanted our new effect system to run on most video cards. And sort of the lowest common denominator in terms of pixel shader versions is pixel shader version 2, which has been out for, I don't know, half a decade now. It's pretty old. It's pretty commonplace. The only hardware you wouldn't see this on would be on some more recent notebooks. All the recent notebooks should support this because any notebook that can run the window manager in Vista and have the blur behind the window chrome, that's all using Pixel Shader 2. So any video card that can do that is a Pixel Shader 2 video card. So it's only kind of sub-notebooks and kind of cheaper laptops that aren't going to support Pixel Shader 2. And those are where you're going to run into the software fallback. So in exposing our new effect system, here's how we changed the class hierarchy. You can see both the new effect and the original bitmap effect have a common ancestor in animatable. I drew a red line through BitmapEffects, so don't use it anymore. We've got the new effect here in blue, and we have the blur effect and drop shadow effect, which were the re-implementations of the original blur bitmap effect and drop shadow bitmap effect. And we would encourage you to use those instead of the old APIs, just because these are the way of the future. And then we have this other class called shader effect, which you derive from when you're implementing your own custom bitmap effect. So a few more design characteristics here. We decided to not extend the original BitmapEffects API. You can see that we created this new API. We didn't just derive from BitmapEffect and create some kind of a shader BitmapEffect. And the reasons for that were because it would be extremely difficult to get intermixing of old and new BitmapEffects to work properly. If we had an effect or a BitmapEffect group and you stuck an old BitmapEffect and a new BitmapEffect into it, it would be difficult because we'd be rendering into a software intermediate render target. We had to suck that into hardware, render with hardware on it, suck that back into software to render more software on it. So it would have made the entire pipeline extremely difficult for us, and the performance characteristics would have been terrible. So that's why we went the road we did. We just said we'd start over with a clean slate and do it properly. So the takeaways from this are that if you're using outer glow bitmap effect and Boss or Bevel, you're not going to have a new hardware accelerated implementation of this. And in fact, when you move to WPF 4.0, you're not going to get an implementation of this. You're going to either have to write it yourself or just find some other effect to get the effect you're looking for. You can actually simulate outer glow with a drop shadow if you set the offset to 0 and you make your radius large. So you can pretty well approximate outer glow. It's not exactly the same though, but I don't know. Sorry. Going through this, we added a new property you can query to determine if your machine has our software fallback mechanism or not. If you don't support SSE2, then you can't run with software fallback. So we allow the application to query this with the render capability that is shader effect software rendering supported property. It's kind of a mouthful, but it gets the job done. Something else to note is that there's no effect group in our new effect system. In the old effect system, you had a bitmap effect group, and you could just stick a bunch of bitmap effects into them, and you could apply that whole group to a UI element. Now what you have to do is you have to nest elements, and you put one effect on each element. And I'll show you the nesting before I show you the demo. So this is what the nesting would look like. You can see I've got a grid, and I've called it grid 1, and I've got an effect on it, which is a blur effect. And I've got inside of that a grid called grid 2, and I've got a drop shadow on that. So this is how you compose effects if you want multiple effects. Anyway, back to the demo I'm going to show you. If I can get the KVM switch working. Just kind of want to show you a quick demo of what you can do with new effects. And I'm actually using some borrowed code here. That's not my machine. There's that. One day I'll find it. This was working a second ago. Give me 1 second here. I think Vista's fighting with the KVM switch here. This is Murphy's Law when you're in a talk like this. Give me 1 second. I got to get this working because I have other demos I want to show you. And that's not it. I'll try disconnecting and reconnecting here. There we go. I think that might be it. Or it might not be it. I'm sorry? You know, if that works, I'll be very... All right, so here's... no comment. Here's a demo of what you can do with the new effects. This is actually code I borrowed from Tamir Kaysen, who I just met here a few days ago. Oops. Shift F5. Let me just run this. So Tamir wrote code that would extract a webcam output, and he would stick it into an interrupt bitmap. And so what I'm doing is I'm applying a series of bitmap effects to that interrupt bitmap. And so you can get effects like this, where you're basically composing multiple pixel shaders on top of your webcam output. So what I'm doing here is I'm first doing a blur, and that's reducing the high frequency content of the video output. And then I'm doing sort of a color space conversion and a color quantization. Then after that, I'm doing an edge detection. So you can get pretty cool effects. I was actually going for like a cartoon-like effect, and if I'd had another couple days, I think I could have gotten it working. But I don't know. I'm pretty happy with the effect anyway. It's kind of a cool webcam effect. And it just goes to show you, I mean, these are a lot more powerful than just doing blurs and drop shadows. You can kind of really get kind of very cool effects out of the new effect system. So there's my demo. So. Now it'll take me 20 minutes to get back to the slide deck, so watch out. I need to put the hat back on. There we go. Okay, so the core of our new effects system is pixel shaders, and I'm going to give you kind of a brief primer of what pixel shaders are. I don't want to pretend this is kind of the be-all end-all of pixel shaders, but if you don't have any exposure to them, hopefully you'll leave today feeling like you have some understanding. So what a pixel shader is basically is a tiny program that's run by the GPU, and it's designed for maximal parallelism on the GPU. It's a program that's run once per destination pixel on your screen, and it's run in destination space. So when you're drawing something on the screen, there's actually a little pixel shader program running for each pixel that's drawn on the screen. They're typically used in 3D rendering systems. They're used in games a lot. They've been around for years. It's only kind of a recent advent that they're being used for kind of desktop applications, and we're kind of blazing the trail with a lot of this stuff. They use a concept called SIMD, which is single input, multiple data. So the idea is you can do a single operation like an add or a multiply, and it'll operate on multiple pieces of data at the same time. This is a concept that's not new. SSE, SSE2, these were all sort of SIMD instruction sets that have been used for media optimization. And because of the way graphics works, you're typically doing the same thing to a lot of pixels at the same time. You'll multiply each color channel by the same value. So it makes a lot of sense to have these parallelism constructs built into the language. In pixel shaders, there are several data types. The PS2.0 version that we're using doesn't have most of these. I believe it only has float, but I might be wrong. But there are, in the more advanced versions, there are bools, ints, uints, floats, halves, doubles, which are just basically the lengths of the floats. There are vector types, which are kind of SIMD types, like a float4, which is the example I'm showing on the slide. You could have like an int4 or a float2. It's basically two pieces of data that are combined into a single variable. And I guess the last bullet point, when you run the shader program, it's run thousands of times. And it's actually being run in parallel. If you'll hear people talk about how many pixel pipelines a GPU has, that means how many pixels it can be running pixel shaders on at the same time. So people talk about CPUs having 4 cores, 8 cores, 16 cores, but GPUs have hundreds of cores. And it's just the fact that they've constrained the programs that run on the GPUs is what allows them to get such massive parallelism. Pixel shaders were originally written in an assembly-like language. It was difficult to use. There were different versions per hardware vendor. It's been standardized now pretty well. Direct3D uses HLSL, which is the high-level shading language. OpenGL uses GLSL, which is the GL shading language. They both look a lot like C if you look at them, and I'll show you examples in just a second here. The big difference is, syntactically, they're very similar. HLSL, you first compile into a byte code, and then you send that byte code to the video card, which consumes the byte code and runs it on your screen. In OpenGL, the video driver itself actually has to have the shader compiler built into it, so it's kind of a larger task for the driver manufacturers. So as I alluded to before, there are several versions of HLSL. These are kind of the high-level limitations of the different languages. There are a ton of limitations that I'm not listing, though. But WPF supports the 2.0 version. You can see that the limitations are quite a bit lower than they are for 3.0 and 4.0. Pixel Shader version 2.0 was introduced with, I think, DX9. 3.0 also came out with DX9, and 4.0 is a DX10 only version. So you'll see a lot of DX9 cards will have PS3.0 support. Right now, there's no ability in WPF to use that, so you're limited to 2.0. If you look at kind of the other constraints on this chart, you see instruction slots and executed instructions. And in 2.0, that's the same. In 3.0 and 4.0, that's not. The reason for that is because 2.0 doesn't have true looping constructs. It doesn't have the same kind of flow control constructs that 3.0 and 4.0 do. So in 3.0, you could have a program that's only 10 instructions long, but it loops through itself 1,000 times. So your overall executed instructions will be thousands of instructions. Whereas in 2.0, I believe it does loop unrolling when you actually go and compile the shader. And then constant registers, which I'm going to talk about more here. You can see there are 32 constant registers in 2.0, and there are a lot more in the other languages. Constant registers are basically how you give data to the pixel shader. You can give it floats, or you can give it other data, and then the pixel shader will use that in addition to the data it gets from the source textures that it's reading from. There are a number of intrinsic functions built into HLSL. This chart actually includes the ones, I believe, that are in DX10, so it includes the PS4.0 instructions. I couldn't get a list that only had the DX9 instructions, but you can see there are a ton, and most of these, I think, will be exposed in PS2.0. I haven't actually gone through each one and tried to figure it out, but it's a very powerful language. And to get down to code, here I just want to give you an example of these vector types I was talking about. This is very C-like, except instead of a float, you've got a float for. It's like an array of floats, basically. So you can see the first line, I've got this thing called myColor. I'm defining 4 floats for it. And then I've got this other thing called color filter, and I'm defining a bunch of floats for it. And you can see with a single multiplication, I'm actually doing what's effectively a dot product between those two float fours. I'm doing a piecewise multiplication. And down here, you can see my result is basically the result of multiplying each of those two together, which is why the first 2 color channels are zeroed out after that multiply. It's very fast to do this on the GPU. It can do this, I think, in like 1 instruction or 2 instructions, whereas having to serialize each of the multiplications would be a lot slower. And you can address the subcomponents of these float fours with different subscripts. You can address them as .x, .y, .z, and .w, or .r, .g, .b, and .a, because you can use them either as coordinates or as colors. And so those addressing modes are built into the language. There are matrix types. You won't be using these too much in WPF shaders, but they're there. You can define, I think it might be up to a 4x4 matrix. Maybe you can define larger than that, but I really haven't had much need for these. But they're there if you want to use them. So getting back to what shaders can do, they're basically reading from source textures. They're getting inputs from these shader constants through the shader constant registers. And they don't just have to read from a single source texture. They can read from multiple source textures. We typically refer to that as a multi-input shader. I'll go into this in a little bit more detail a little bit down the road. But they read shader constants. PS2, I believe, only allows floats, has scalar and vector types. Something else that's interesting and that you should know about is that all of these things are numerically indexed. You have shader constant registers, and you refer to them by the index of the register. So you'll have register 0, register 1, register 2, and you're putting floats or whatever into those registers. And the way they're exposed in WPF, on the managed layer, you decide which shader constant register you're going to put the values into just by a number, and then in your HLSL, you have to make sure your number maps correctly. So you'll see this in a minute, but you just have to make sure the numbers of the shader index registers match between your HLSL and your managed code. So here's how you read values from shader constant registers. And again, this is disjointed code. I'll show you a little shader program in a minute. But you can see I have this register keyword, and I've got these letters C0, C1, C2. Those are defining the shader constant registers that I'm reading from, and the number is the index. You can see I have a float2 called mouse position that I'm reading from shader constant register C2. I can get just the x position from that by just .x on mouse position, and that's a single float, which I can load into my mouse x position variable. And here you can see I'm doing a multiply between width and height, which are both floats, and then I just get another float out of that. So it's just like C, basically. Very simple. So as far as samplers are basically how you read from a source texture. They're also numerically indexed. In WPF, we allow up to 4 source textures. So people will talk about multi-input shaders. That means a shader that's got multiple samplers. We call them multi-input. I'm just kind of going through my slides here. We have a notion of an implicit input, which is basically we will create a sampler for the element on which you're applying your effect, even without you having to do any extra work. It's just sort of created there for you, and you can use it if you want. You don't have to use it if you just have a generative shader that maybe is just taking input in the form of shader constant registers, and it doesn't need to read from a source texture. And I'll show you the syntax for reading from textures. You define this thing called a sampler 2D, and here the name for this thing is implicit input sampler. And it's coming from the zero indexed sampler. And here I've got a float 2 called texture coordinate. I'm just giving it 0.4 and 0.6 for the U and V coordinates. Again, in texture coordinates, you're going from 0 to 1, and that's pretty standard. I'm assuming everybody knows that. You can read from the sampler with this text2D keyword. So you're basically reading from the implicit input sampler at coordinate text coordinate, and then the result of that is a color, which is this float 4. Pretty standard, and it's a float 4 again because it's got RGB and alpha. It's not just RGB. So here's a very quick example of a very small shader program. It's just going to remove the red and green color channels from an image. That's it. It's very simple. You're just defining an input, your input sampler, which here is just called input. It's in the 0th index. And then you have this tiny little program. This program returns a float 4, and you can see down at the bottom of the program it's returning color, which is obviously a float 4. All it's doing is it's reading the value from the UV coordinates that are given to it, and then it's setting the red and green color channels to 0. And you can see the way I indexed color.rg, you can index multiple values and just set them all at the same time, so it's easier than doing them separately. And here I kind of go through, I already explained all this, I'm not going to bother dwelling on this, that just explains every line of the program. So what else do you need to get this stuff to run in WPF? I've just explained kind of how the HLSL works, but there's also this manage component that I keep talking about. I haven't shown it to you at all. Here's what it looks like. This is a very basic one, and I'm sorry for the small font. You can blame the people who made the slide templates. It's not my fault. So. Basically, a lot of this is just boilerplate code. The only stuff you really have to care about, you can see this brush called input. It's kind of at the middle of the slide. That's just basically the input sampler that your shader is going to be reading from. And you can get and set it. And then you've got a dependency property that's exposed. That's just the input. You can see this is the dependency property syntax down here. It's second from the bottom line. It's kind of ugly. But you see there's a 0 at the end. That's defining the sampler index that this is going into. So it's going into the 0th index, which if I go back, oh, this thing is pretty slow. Okay, you can see register S0, very top line. So it's the 0th index that the sampler is going into. And you can have up to 4 again, so it would be 0 through 3. So you're sticking this input brush, your sampler, into the 0th index, and then that's about it. The rest of it's all just boilerplate code. So then, having done that, how do we actually apply them to your scene? The same way you would with BitmapEffects, except instead of the word BitmapEffect, you've got the word effect. So you've got grid.effect, then you're just setting my effect on it. And same thing in code, you just have a grid, and then you just create a new my effect, and you just set it as the effect property on your grid. So it's very easy. So kind of going through the steps again, this is kind of the kind of all-up overview of how you do this. You would write your pixel shader in HLSL, then you derive from the shader effect class. You expose whatever DPs you want to be accessible from your shader effect. And the ones I've shown you just now didn't really have anything meaningful to expose, but I'll go and code one up in a minute that will. And then you just compile your shader effect. There are kind of two ways to do this. One is to go through and do a bunch of boilerplate code yourself. The other way is to use a shader build task that we've actually published that's on CodePlex. Greg Schechter and Gerhard Schneider, who are both on the graphics team, wrote this. It makes it extremely easy to write shaders, and I'll demo this in a second. And then you just apply it to your element, and you're done. So a couple of last-minute details before I get down to kind of doing kind of a little bit of coding. WPF deals with pre-multiplied alpha internally. What this means is that when we have a color, it'll have an RGB and alpha components to it, but we've already multiplied the RGB components by the alpha component. So if you're going to use this in your shader, you have to unpre-multiply the alpha from the colors. And all that really means is you're taking the color and you're dividing, if you look at this unpre-multiplication step here, you're just dividing RG and B by the alpha of the color. So that unpre-multiplies the color. And then when you're writing the color back out, you have to re-pre-multiply it. And again, I'm sorry the syntax is kind of confusing here, but you're just basically multiplying RG and B by the alpha value. And this is pretty standard. You can just look up pre-multiplied alpha online, and it's typically done as an optimization. That's why WPF does it internally. So just remember to, if you care about transparency working properly, and if you have everything in your scene is completely opaque, it doesn't matter. I'm actually not doing this in the shader that I demoed to you guys a second ago. So it doesn't matter in a lot of cases, but if you wanted to handle cases properly where there's transparency, you have to remember to unpre-multiply your alpha and then re-pre-multiply it. Another last-minute detail is this horrifically named property on the shaders called DDXUV DDYUV register index. What this is doing is, in a lot of shaders, it's useful to have the partial derivatives of the source texture as you progress down through writing the destination pixels. And I was trying to think of a very succinct way to word this. What you see is this big quote here I just copied straight from MSDN because it was a very succinct explanation of how this stuff works. Basically, I'll just read it for you. If you step one pixel to the right in screen space in the X direction, then DDX of U is the amount that U changes in texture space, and DDX V is the amount that V changes in texture space. If the effect is axis aligned when it is rendered, then DDX V is 0. If the effect is rotated when it is rendered, then DDX V is non-zero. So most effects don't have to worry about this. This is useful if you're writing an effect that actually worries about how you're progressing through the texture space as you're rendering the effect. There's an effect that has been pretty widely publicized that we had in WPF that was called the brick mason effect, where it basically pixelated the whole scene and you had these like brick seams. And that was using this register index. The reason it's called register index is you're assigning the pixel shader constant register index that we're going to write these values into, if that makes sense to you. So if you were to put the number 12 there, then shader constant register 12 would have these values, and you could read them out as like a float 2 or a float 4 in your pixel shader. I typically don't use this, so it's not something you really have to worry about when you're initially writing shaders, but just be aware that it's there. Something else about this is it's actually exposed as a property in Pixel Shader 3 and Pixel Shader 4, which is why, I mean, people do use this. In Pixel Shader 2, it's not exposed as an intrinsic in the language, so you have to go and, that's why we basically give it to you, in case you want to use it. And something else is this effect mapping property that exists on pixel shaders. The reason this exists is because you can not only do color transforms in pixel shaders, but you can do spatial transforms. And when you're doing a spatial transform, you need a way to reverse map the mouse hit testing properly through the shader. You might have seen some of the demos we've got where we're doing kind of bulge effects, or where we're doing swirl effects, or where we're doing magnify effects. If you're not reverse mapping the mouse coordinates, then you're basically doing a mouse pass-through, and you're assuming that there's no spatial transform. So what you do here is you implement a general transform You derive from general transform. You write your own inverse mapping. You can just write that in C# or whatever. As long as you have an invertible function that your matrix is performing, then you can invert it. It just takes a coordinate and it outputs some different coordinate. So you basically have reverse mapped your shader. And then that's how you get the inverse mappings to work properly. And here's a quick demo, assuming I can get my laptop to project again. And I have little faith that I can. But I just want to show you kind of how to write a pixel shader using the build task. So give me 1 second here. See if I can get this to work. I might need to put the hat back on. There we go. Let me do one more, see if I can mirror it on my own screen. All right, so we want to write our own shader. And this is assuming you've installed the shader build task, and I would highly encourage everyone to install the shader build task. Let's go ahead in Visual Studio, new project. And you can see under My Templates, we've got this WPF shader effect library. So I'll go ahead and just select that. And now it will just pre-generate a very kind of simple Hello World shader for me. If you look in the .fx file, that's where the actual shader code is. You can sort of see this is the entirety of the shader right here. It's just reading a color from this implicit input sampler, and then it's multiplying the result by color filter and then returning that. If you look up here, it's reading this value called color filter from the 0th shader constant register, and then here it's reading the implicit input sampler. So let's go ahead and turn this into a full-fledged WPF application. So let's just create a new WPF application. Let's give it a second here. My laptop is on its last legs. All right. So let's just define this WPF application as the startup project. Inside of this grid, let's stick an image. Source equals, let's do something cute. How about this cat picture I've seen people using? It looked pretty sweet. So there we go. Let's run the project. Let's get an image in a grid. And there we go. So now we want to apply our shader to it. We haven't even done anything to the shader so far. So the shader is just up here. It's this separate little project. Just add a reference to it in our WPF application. So there we go. Now I've got a reference to it. And now just from my XAML, just need to map it in with a namespace. Which is right there. Let's call it EFF. So now image.EFFect. Let's put an effect on there. So EFF effect 1. Now this is what's actually in my shader over here, and you can see the Visual Studio Editor has already applied the effect to my window. I'll go ahead and run this, and you can see what the output looks like. It's doing some kind of a color filter on here. And if you look in the effect again, you can see what it's doing. It's taking the color, it's multiplying it by this color filter. Now we haven't set any value for this color filter, but the C# will put a default value in there if we don't set anything. So if you look through the C#, this is the C# code that was auto-generated by this shader build task. Let me see if I can find where the color is being set. Yeah, down here you see this color filter property. The default color is yellow. So if you don't set anything else there, then the color is just going to be yellow. Let's go back here, and let's say I don't want to use this color filter. Let's say I just want to zero out the green and red color channels. I can just say color.rg equals 0. And then just return that. Now we should wind up with an image that's just got the blue color channel, and there we go. So we've got a pixel shader that just removed the red and green color channels. Now you can get more sophisticated with this stuff if you want to like add another input. So I guess, how am I doing on time here? 2:26. What time is this supposed to be over? 3. Okay, then I'll quickly go through this, because after this I still have to talk about DX interop, so I don't want to spend like the entire day on this shader. But here you see I've got this input. I'm going to add a second input to my effect, which will then interact with the original input. So I had the original brush called input. Let's call this one input 2. I'll call it input 2 property. This is all just dependency property syntax I'm messing with here, so it's nothing super complex. Here I have to change the shader constant register, because or the input register rather, the sampler register, because I'm already using 0. So this one will go into register 1, and I believe that's it. I just have to now. Whoa. Give me 1 second here while my computer freaks out. All right. You can still see that. Good. Okay. So this code up here where I'm calling update shader value, this is part of the constructor. Let's just also call it an input 2 property. So basically when you're doing this, it's just a matter of looking at what's already in the boilerplate code you get, and then just replicating it when you want to add more stuff. So I've just added this input 2 property, which will go into sampler index 1. Let's go over to the actual shader code. You can see where I'm getting this implicit input sampler in register 0 up here. Let's just replicate that. Now we're reading from register 1. Let's call it other sampler. Down here, I read this color from this first input sampler. Let's read another color from this new sampler we've got. The sampler is called other sampler, so let's go ahead and read same coordinate as that we're reading from the other one at. Let's call this thing color 2. And now let's add the 2 colors together and return that color. So we'll do color plus equals color 2. Oops, color 2. So now I believe my shader should be good to go. Let me just go ahead and see if it builds properly. So yeah, the shader part built properly. So now I just want to add another input to the shader. And it's going to be something that's going to be added to the original color. So I'm going to go ahead. I've got my effect there. Sorry. Effect 1. Can I get this syntax right here? Now I've got this thing called input 2 that's exposed, and that's just basically a brush. So I can stick any brush content in there, and it's going to work with my shader. So let's go ahead and stick a visual brush in here. Everybody loves visual brush. And then that visual brush will have inside of it a media element. If I can, oh, visual brush, that visual. There's a media element. Source equals, and now I'm sure I've got something in the root of my folder here. Let me just find anything. Here's, how about this? How about adrenaline rush? That sounds exciting. So source equals this adrenaline rush video. I'm going to go ahead and mute it because I'm sure it's got too much adrenaline for me. And now let's go ahead and see if this runs. It is running, and there we go. It's playing a video. The shader is adding the color of the video to the image. And that's what you're seeing right here. It's a multi-input shader. Let's go ahead and do something a little bit more interesting. So I've got this input color, which is my the cat texture. I'm going to go ahead and instead of reading from just UV, I'm going to offset that by the color here. So it's going to create some kind of a weird effect, but basically I'm reading from the first texture, and I'm going to tweak the texture coordinate of the second texture I read based on the first texture's color. So let's go ahead and read and sample from UV plus color.rg. I believe that should work. So now you can see that there's sort of a weird effect going on. And this isn't anything I kind of thought up ahead of time. This is just something I sort of whipped together, but I don't even know what that's doing, actually. It's doing something weird. I mean, but you can imagine what you could do with this stuff. You can, if you want to do something else easy, let's say I want to, let me Control-Z that. Let's say instead of adding the two colors together, I want to add the color of the cat plus the inverse of the color of the video. I can just do 1 minus color 2. Actually, let me do one thing. Let me make sure that that the alpha channels are going to be correct here. So color 2 equals float 4, 1, 1, 1, 1 minus color 2. Color 2 dot A equals 1. So just you have to worry about alpha values when you're doing this stuff. Otherwise, it can get pretty tricky. So just watch out. So now I'm basically taking the inverse of the color of the video and I'm adding that to the other color. And let me just make sure that the final color has an alpha value of 1, just because I don't know what else it would be. So that looks different again. So I mean, again, your possibilities are endless. This is just, I mean, it's another programming language you can use with WPF. I don't want to kind of spend too much time mucking around with this stuff. But you can do all sorts of stuff with this. It's very powerful. And yeah, I'm going to go back to my talk and go on about DX interop now. So yeah, so let me switch over to the other machine. Okay, D3D interop to change tracks completely here. Prior to D3D image, which is the new class we just introduced in the service pack, if you wanted to interop Direct3D with WPF, your options were pretty limited. You basically had to use HWind hosting in WPF, and HWind hosting has a large number of caveats, the biggest one being this so-called airspace issue, where each pixel is either owned by your hosted HWind or it's owned by WPF, but it's not owned by both. So you can have a big rectangle that's got D3D content that's in the middle of your WPF application, but you can't draw alpha blended text on top of the D3D content. It's basically an all or nothing proposition. It's either D3D content or it's WPF. So you couldn't do things like fill a button with D3D content, because then you would have airspace contention between the button and the D3D content. So with D3D image, we've solved this. What you do is you basically create your own Direct3D device, you render your content to it off screen, and then you give us a pointer to the surface of that D3D content, and we'll copy it over and we'll use it in WPF like we would any other content. So it's, as far as we're concerned, it's just like having like another intermediate render target that's in hardware that we can just read from and then consume in the framework. Something that people have requested a lot and we still don't have is the reverse, where WPF is outputting D3D content that then your D3D application will consume. That's something we'd like to enable. It's difficult to do it in a way that's going to be forward compatible, though. So we're thinking about it, but it's not currently on the books to be done. So this D3D image class, we derived from image source, and we just stuck it right there. So it's pretty easy to use. It's in a new namespace, or not a new namespace. It's not in one of the standard namespaces, though. It's in the interop namespace. Now this matters because it's not part of the default XML namespace that you get when you just like load XAMLpad. You'll try to instantiate a D3D image, and you can't because it's not part of the default XML namespace. So you have to go and make sure your namespace is mapped properly. So here's kind of the order of operations when creating an application that's going to use D3D interop. I'm going to kind of go through this quickly again because we don't have a lot of time here. But basically, your app will create a D3D image. Your app is going to create this unmanaged Direct3D device. The Direct3D device is going to be rendering to an off-screen surface, so that device just creates a surface. You hand that surface to our D3D image via the set back buffer method. Then your app will just render D3D content to the surface. It has to lock the surface, render to it. Then you add dirty recs to it, and you unlock it, and you give it to us. And after unlocking it, we'll, in the background, suck the bits from the surface. We'll use them, and you can continue to party on your surface as much as you want. We worry about redrawing things. You don't have to worry about that. Whenever your D3D image is dirty, we will go and as soon as possible, we'll read the dirty bits from it and draw them. Here's a quick little drawing. This is again from, I think this was from NSDN. It just kind of shows you how it's working. You've got fundamentally two threads in WPF. You've got the UI thread and the render thread. The UI thread is where the D3D image is owned. So you've got a D3D image. It's got its own back buffer. You're copying forward to the front buffer, which is conceptually owned by the render thread. And the render thread will also notify you when the front buffer availability has changed. And I'll go into that in a minute because that's another can of worms in itself. Here's some pseudocode for using D3D image. You can see, I don't want to walk through the whole thing in excruciating detail, but you're basically creating a D3D image. You're adding an event handler to find out whether the front buffer availability has changed. And again, I'll talk about that in a minute. Whenever your surface needs updating, you're just locking the surface, rendering to it, adding dirty recs, and then unlocking it. When you find that the front buffer availability has changed, there's a bit more work you have to do, which is basically you find out if it's available, and then you can go and keep trying to lock the surface, and you render to it. So without getting into too much more detail, I'm just going to show you a quick demo of what you can do with D3D image. This is actually not something I wrote. This was written by Mark Smith, who wrote the D3D image lab that we had in the labs section of PDC. And it's also going to be available on Codeplex after we're done with all of this. So I found I have to unplug and replug my laptop in order to get the KVM to actually see it. So give me 1 second here. There we go. One more. So here's a finished application that's using D3D image. And I mean, the things you should look for is the fact that not only does the alpha blending work between the WPF content and the D3D content, but you can also, ouch, I wasn't expecting that. Actually, wasn't expecting that at all. Let me see if I can just find a binary of it that's already compiled and running. This worked a second ago. Interesting. All right, maybe I can't show this to you. This is my demo machine from hell. This worked 20 minutes ago, but let me try just closing this and reopening it. And if that doesn't work, then I'll call it a day because it's not critical that you see this. Again, this is all from the lab. But it would be nice to kind of just show you a demo of it. I've got other demos I could show also. No, interesting. Give me 1 second here. Let me. Try that. Actually, if I re-extract it, I'm sure it'll work. Just bear with me here. Close that also. All right. And again, this is something, after the fact, I'd highly encourage you to download this from Codeplex if you want to, or windowsclient.net, wherever it's going to be available, because it's a very thorough lab. It shows you how to do everything I'm talking about here in much more detail. This doesn't work, I think I'll put my hat back on. So, Yeah, I think it's building. Let's give it a second here. Oh, I gotta set the, sorry about that. Set the startup project. Go ahead and build again. There we go. So here's D3D content that's being rendered behind WPF content. You can see the alpha blending is working properly. You can tell it's D3D content because WPF 3D doesn't have rendering constructs like wireframe, whereas D3D does. People have been asking for this for a long time. And since we don't have wireframe, it's now possible to just have D3D exist as a first-class citizen in WPF. Something else that's interesting about this, let me zoom in on this a little bit, is you can go ahead and apply effects to this. Now that we have these hardware accelerated effects, and now that all of this is in hardware acceleration, I can apply a drop shadow to this. And it's actually applying the drop shadow to the D3D content. I could blur it. So that's, again, a hardware accelerated blur that's being applied to hardware rendered D3D content. And we're hosting the whole thing in WPF. Or here's another one. This is a wave that you can apply. This is this is a productivity enhancing shader right here. So I would encourage, if anyone from AutoCAD is in the audience, you probably want to add this to your application. And again, it's WPF, so the background doesn't just have to be a solid color. You can make an image, you can make it a video. I don't want to go into too much detail over this, but it's pretty cool. It's a pretty cool feature. And here's a drop shadow again. I can go ahead and make the shadow really deep or whatever. I mean, you get the idea. It's fully integrated. It's a first-class citizen of WPF. And down here in the corner, you can see this little preview. He's basically able to use a visual brush on the D3D content, and it all works properly. So that's where we are with D3D image. Let me switch back. Finish my talk here. So there are a few gotchas with using D3D image. One is that there are two types of D3D9 devices you get depending on whether you're on XP or Vista. It's because the new Vista driver model introduced this notion of a D3D9EX device, which allows for shared surfaces, which is a surface that you can basically share between two DX devices. It makes it very efficient for us to get the contents from your DX device and consume it in WPF. If you don't have a D3D9EX device, which means you're using an XP driver model, either on Vista or on XP, we have to go through a more elaborate step where we will copy the bits of the surface from your DX device to ours. And we try to do that in hardware because we found we can use effectively a GDI blit to copy from one DX device to another. It's not the most efficient way to go, and a lot of times it's not even hardware accelerated. So sometimes we'll actually be sucking the bits back into system memory and then copying to the other DX device via system memory. So by all means, try to make a D3D9EX device if you can, and if you can't, then you use the regular D3D9 device. And this is all, again, in the lab. It shows you how to do all of this. Something else to worry about is the pixel format that you choose. Different pixel formats are going to have different hardware acceleration performance characteristics. You can see all the large fonts here are hardware accelerated, where I've got small fonts. This isn't hardware accelerated. This chart, again, is from MSDN, so you can find this online, but it shows you that your choice of pixel format is very important depending on which operating systems you care about running on. You can see Vista with WDDM, which is the new driver model, and a 9EX device is always going to give you hardware acceleration. But when you're on XP, your mileage will vary, so be careful with what you choose. Your D3D device can be lost at any time. This is why you had this availability change notification that you subscribe to. If you saw in my pseudocode, you're subscribing to this notification. Whenever you lock the screen, you'll lose your D3D device. When you run a full-screen exclusive D3D application, you're going to lose it. When you do user switching, remote desktop, there are other conditions. So you have to be able to handle this condition of losing the D3D device. Otherwise, your app would break the first time you locked your screen. That's why we have all these notifications. So basically, when you lose your device, I don't want to go into this in too much detail again because it's all available online and it's got more detail. But you basically subscribe to this event. When the device is lost, we're going to release our reference to the back buffer. So you're going to have to reset the back buffer with your device once you're able to use it again. And that's about that. A few other recommendations is you should create a multi-threaded D3D device. You should set the FPU preserve creation flag, because otherwise we can run into precision issues where the FPU precision is different between us using D3D and you using D3D. On multi-mon XP systems, something else to think about is when you create your D3D device, you're basically giving it monitor affinity. I think there's a creation flag that you give it. And so on XP, it's very expensive to render to, let's say, your primary monitor and then copy those bits to your other monitor when it's actually time to draw the D3D image. So what you can do is create a separate DX devices, one for each monitor, and then figure out where your application is on the screen. And depending on where it is, you'll render with one DX device or the other, and then you'll give us the back buffer that corresponds to the device that your application's screen is on, if that makes sense to you. It's kind of a mouthful. But basically, you want to keep your DX device on the same adapter and on the same screen that your window is. And that's about it for D3D image. Now here are my 2 slides about WPF futures. I promised I'd give you something. It's not going to be much more than you've already gotten. But here it goes. In the future, we're looking for increased graphical richness. We'd like to enable PS3.0. I can't say for certain whether it's going to be on the next release of WPF or sometime farther out in the future. We'd really like to enable it. There are a few caveats to doing this. One is that we try to have everything have a software fallback pipeline. But if you remember from 20 slides ago, Pixel Shader 3.0 allows for much more complex application or pixel shaders than PS2.0 does. So a software fallback of a PS3.0 shader could take minutes to render if you have a full screen. So this is something we're worrying about. We might end up doing hardware only. We're not entirely sure how we're going to do it. We might have some kind of, there might be other mechanisms we'd use, but there are caveats to doing that. In the future, we'd like to offload more work onto the GPU. If you look at when WPF was originally conceived, most GPU hardware was fixed function. That's almost entirely gone away now. Most hardware has a programmable pipeline, and with the advent of stuff like DX10, we have substantially more capable programmable pipelines. So it's in our interest to move everything to the GPU that we can. So we're going to look to move stuff to the GPU for the sake of dramatically increasing scalability. We'd like to improve rendering quality. One of the things we're trying to do is we're trying to integrate with DirectWrite for our text rendering. It's the new text rendering APIs that the WEX guys were gracious enough to create, and they're very hot. I recommend you check them out even if you're not going to use them for WPF, if you're just going to use them for an application that's going to be run on Vista and Win 7, because they're very hot APIs. So we'd like to use that. I'm, again, not going to give you definite dates about when this stuff is going to happen, but we've heard complaints about WPF's text rendering quality, and we're doing our best to address them. Another feature we're adding is layout rounding. One of the consequences of our per primitive anti-aliasing is that you can actually get seams when you get abutting shapes. And what I'm talking about is if I have 2 rectangles and they share an edge, you can get a seam on that shared edge, because we're not rendering our anti-aliasing the same way you would in 3D, where you're basically rendering into a multi-sample buffer, then you're doing a downsample, and then you're using that. What we're doing is we're anti-aliasing each primitive, and you're getting color contribution from the background, even if you shouldn't on these abutting edges. So layout rounding should fix that, because primitives will be snapped to pixel boundaries. This is a feature that's already in Silverlight, I believe, or it's going to be in Silverlight very shortly, and WPF will have it too. So moving forward, better exploitation of hardware and other potential stuff we might do, and this is just a list of stuff that we have not committed to at all. So just consider this to be things we're thinking about. We'd like to do some sort of vertex shaders. We'd like shader groups. Shaders in 3D would be nice. We'd have to figure out a way to do it. We'd like to do 3D improvements. We're already doing some performance improvements in 3D, but we'd like to do a lot more, and we'd like a more extensible media pipeline. For more info, I've got some pretty useful links here, and you can get these after the fact if you download the slide deck. Greg Schechter's blog. Greg Schechter is the graphics architect who was responsible for a lot of the stuff you saw tonight. He helped write the shader build task and a bunch of other things. Go to his blog. He's got tutorials on how to write shaders, and they're a lot more thorough than what I've shown. The Visual Studio build task I showed you for shaders is extremely useful. You can get that from Codeplex. It's pretty easy to find. You can get a link to it from Greg's blog, so you don't have to waste your time downloading my slide deck. We've published an effects library. It was the result of work from a lot of our devs and testers. It was compiled by Troy Jefferson, who was an intern who worked with us for a few months. You can get that from CodePlex. You can get the D3D image and shader labs somewhere on windowsclient.net. I'm told they're in windowsclient.net/WPF. So go there, and you should, if not now, very soon be able to find this stuff. And there's a pixel shader editor that allows you to edit shaders in real time and try them out, called Shazam, that I've used very briefly, but it seemed pretty hot, so I'm plugging it here. So go ahead and download that if you're interested in playing around with shaders. And that's it for my talk. I'm willing to take questions. I'm looking forward to evals, and if there are questions, go ahead and go to the microphones, and I'll address them. So,
Hi.
Question?
So yeah, the first shader I tried to write was, it worked, but I ran into a problem. I'm wondering if there's a way around it. It was a kind of tessellation thing. I wanted to do a hexagon-shaped tessellation thing, and it worked, but I was getting a lot of aliasing in highly detailed areas of the source image. So what I wanted to be able to do was kind of de-res the source image. You know, in DirectX, they actually have a way of doing this. You can ask to tell the sampler to use like something further up the bitmap chain, and it will give you, you know, a lower frequency input image. Is there a way to do that from the HLSL in WPF? Because when I tried all the things that are supposed to do that, none of them seem to work.
The closest, there are a couple things you can do. One is you can define your input sampling method. There's nearest neighbor or bilinear that you can select. And I think the default's going to be bilinear, so you probably already had bilinear, which would reduce aliasing from nearest neighbor.
Yeah, but I'm talking about sort of reducing, right, you know, like 40 pixels down to 1.
Right, yeah. I think you would have to use a render target bitmap and render your background into a smaller image. That's because I believe we auto-size the intermediate render target that we're sampling from to match the destination size. So.
Okay, so I should stop looking for the right way to do it then.
Yeah, I think that's something we sort of didn't really think about. So yeah, I mean, if you could, I guess, just go ahead and email us after the fact and give us kind of an outline of your scenario. There might be some easy way to do it, but my off-the-cuff answer is to use a render target bitmap and just set the resolution there and then use that, assuming it's not like inanimate content. If it's animate.
Yeah, it wasn't, but that was I'll email you. Thanks.
Okay, sure. Question over here.
So I'm excited to see the DirectX 3D stuff becoming kind of a first-class citizen. I was wondering if there's any similar plans for Windows Forms controls to become first-class citizens.
I don't have any detail on that, so if there is, I wouldn't know about it anyway. So, so sorry.
Okay,
yeah, I'm not aware of anything to that extent. So,
okay, thank you.
Sure. Question back there.
Yeah, we're real interested in the D2D and the direct write stuff, and I was wondering, it seemed like because they use different DirectX surfaces, there might be some interop issues. I guess I'm just suggesting for the future that maybe you guys make it easy to interop the D2D stuff with WPF.
Yeah, we're actually very interested in D2D. It's a very hot API. The big limitation now is that D2D requires DX10, and WPF has to be able to run on XP. So eventually, we probably will be moving WPF to DX10, and at that point, we'd love to kind of embrace D2D as wholly as we can, and maybe we'd even build on top of D2D, but that's way far out in the future. For the immediate kind of 2 or 3 years, we're going to be, I mean, we have to maintain XP compatibility. So, but that's definitely, that's front and center on things we're talking about internally, so you're exactly on the right track. Question?
Yeah, we'd like to see on the effect tag, well, the new one, conditional. So it's based on rendering tier or hardware capabilities or stuff. You want the effect there if the hardware can do it, if the user isn't remoting with remote desktop, that kind of stuff.
Right.
And not just have it always there.
The one thing you can do is there's a hardware-only flag you can set on the effects. So you can basically force it to not use the software rasterizer.
And so if there's no hardware,
it's just no op.
No op.
Yeah. So that might do what you want.
That might do it. All right.
So
thanks.
you can give that a shot. Question?
Yeah. Along the lines of that, I was also thinking the remote desktop is probably the biggest usage case where hardware wouldn't be available. I saw a headline somewhere this week that Windows 7 version of Remote Desktop might allow D3D forwarding. Is that true? Would that enable these sort of effects to be forwarded over Remote Desktop?
I guess I don't want to speak for the D3D team because we've got a D3D expert over there. But it's something you can't do with DX9. So it would. I don't know if Anantha wants to go and answer the question in the microphone. That might be the best way to go about it.
I can answer that question. So the version of D3D that will be remoted via primitives. Actually, D3D9 and D3D10 have bitmap remoting. So D3D10 is the one which will be remoted via the primitives.
Yeah. So until we move to D3D10, we're stuck with bitmap remoting. So it's just where we're at. Any other questions? Nope. Well, thank you for coming.